All right. Sorry for the brief delay, everybody, but thank you so much for joining us. I'm very excited. I think this is one of those presentations that will be very meaningful to me. And so I always love those. But let me just briefly introduce our host, and then I'm just going to turn the floor over to her. So we have with us today Dr. Lizbeth Cruz, who is an assistant professor in the Department of Biological Sciences here at ISU. She leads a research laboratory studying how aging affects the regulation of the nervous system and glucose metabolism. Throughout her career, she has been dedicated to educating and mentoring students at all levels, from elementary school to graduate studies. Passionate about physiology, the study of how the body functions, she enjoys sharing how this knowledge can improve our lives. She also believes education should extend beyond the classroom, helping communities understand how science can benefit everyday life. So thank you, Dr. Cruz. I'll turn the floor over to you.
Thank you so much for the introduction. And thank you so much for opening a space to discuss about the aging process and metabolic diseases like type 2 diabetes. I think these two topics, aging and type 2 diabetes, are two of my favorite topics. So I have spent many years just trying to understand what is happening with this connection. Okay? So please, it's the very first time that I am trying to just have a presentation going from very basic things to more complex concepts. So if you would like to just say, okay, could you stop and you could repeat or explain in a different way, I'm more than happy to just stop and trying to do my best to just repeat things or, explaining concepts in a different way. So please feel free to stop in any time, or we can wait until the end of the presentation and we can just discuss together what I show you, okay? Perfect. So when I was thinking in this presentation, I say, okay, what is the first figure I should show, okay? And a month ago, 2 months ago, I was in Mexico. I'm Mexican. And I say, I will start with this image. Do you know what is this image? No?
Stone carving?
It's a stone something. Yes.
Yes, it is the San calendar of the Aztec culture. It's found in the Anthropology Museum in Mexico City.
Yes, it's a calendar, okay? And you can see very old calendar because it was made in stone. So as every calendar, the main purpose of a calendar is a way to just measure time. Because as humans, we know how important it is to measure time for almost every single process in our day, okay? As a physiologist, because I am a physiologist, I am interested to understand how the body works. Time is very important too, okay? So the first message that I want to transmit is that time is a very important consideration when you want to understand how the body works. Usually in physiology, I have many questions and I say, yes, wait, let me know when, okay? Because it depends of the day. Sometimes some process depends of minutes, others years. So time is a very important variable if we really want to understand what is happening in your body. Okay, so in this image that I show you here, I show you the lifespan, okay? And for the purpose of the presentation, very simple way, I decide to just divide this lifespan into processes. The first one that I will call development. And this goes for embryogenesis here to young individuals. But after this part, we have the aging process. An aging process is for mature adults to older adults, okay? So for the purpose of the presentation, I will just focus in this part, okay? That is going for mature adults to older adults. So what do you think is aging? Because I just said that I will just focus in aging process. But let's start just answering a very basic question. What is aging, okay? And aging, the first thing that I will say is a normal process that we all experience over time. And we all experience, no matter if you want or you don't, okay? And it involves some decline in the body ability to function. So what means decline? So decline means, in simple words, that our bodies are less efficient at maintaining or adapting or even repairing itself, okay? So there are changes that are happening as part of the aging process. What is very important, and I always like to just be super clear about it, is that aging is not considered a disease, okay? Aging is not a disease. It's just a normal process that we all experience. But what we know is that the decline that we have observed as part of the aging process in how our body works, it will just help me a little bit here, will increase the risk factor to develop diseases. What kind of diseases? Well, aging is a risk factor to develop, for example, immune diseases, cardiovascular diseases, diseases associated with muscles, neurodegeneration, Parkinson, Alzheimer, but also metabolic diseases. What kind of metabolic diseases? Type 2 diabetes and obesity, okay? So aging is a risk factor to develop diseases. One of them, type 2 diabetes. So let me show you why we think that this aging is a risk factor to develop diseases, and specifically type 2 diabetes. So I will show you the prevalence of the type 2 diabetes associated with 3 different range of ages, okay? So the first one that you can see here, in a population that is between 18 to 44 years old, the prevalence is only about 3%. But the prevalence of this type 2 diabetes increased to 15.5% in a population that is 45 to 64. But if we just analyze the prevalence of type 2 diabetes in a population that is 65 or older, this number increases to 21%, okay? So what you can observe here is just the prevalence of this disease increases with age, okay? So the question is why? Why this is happening? Why the prevalence increases as part of the aging process? But before just going and trying to answer this question, I will just summarize this very first part. And the first thing that you have to know is that aging is a natural process that we all experience. Second thing is that aging is associated with a decline in how our body works. The third important consideration is that aging is a risk factor for developing diseases like type 2 diabetes, okay? So the goal that we have with this presentation is trying to explain why or how does aging increase the risk to developing type 2 diabetes. But to answer this question, we need to just first start thinking in, okay, what are the main problems that can be associated with type 2 diabetes? And when I think in that, I just decide to go for these two, glucose metabolism and insulin secretion. So before trying to answer this question, where I will show you some data, I will just explain what it means glucose metabolism and what means insulin secretion and how we can connect both, okay? So let's start with glucose. So the first thing that I will say that glucose is a carbohydrate. And usually we call glucose as simple as sugar. Why we call it sugar? Because I'm pretty sure that majority of us, we have this table sugar at home, right? The one that we use for baking, the one that we can add to our coffee every morning or your tea or your favorite drink, okay? It's very usual to add sugar to the things that we eat. The table sugar is called sucrose, and sucrose is composed of glucose and fructose. You see, glucose, sugar, and sugar. So this is why we sometimes can just change glucose and sugar in both ways, okay? So where we can find glucose? Well, glucose is a molecule that we can find in vegetables, we can find in fruits, we can find in milk, okay? For example, this little baby that I have here in this image is having breast milk. And milk One of the main components here is lactose. Lactose is a molecule that is composed by glucose and galactose. So many of the food that we have in front of us every single day will contain glucose, okay? Someone in this room like Idaho potatoes? I like Idaho potatoes, right? So what is the main component of potatoes? Starch. And what do you think? A starch is made of a long chain of glucose molecules linked together. Glucose again, okay? So the message I want to transmit right now is that most of the foods that we eat, from bread to rice to fruit to potatoes, will contain glucose, okay? Glucose is a molecule that we can find everywhere in our food. But why glucose is important for our body? Glucose gives our body cells energy to work. What it means? A car uses gasoline to go. The human body uses glucose to go, okay? Is the energy, just glucose will give you the energy to just maintain this body working, okay? And I'm pretty sure you have experienced what happens if you don't have glucose, okay? You are not you when you don't have glucose, and that's true. Sometimes I say to my students, okay, don't talk to Liz. Liz needs to eat lunch first, okay? If you want a positive, result in a meeting, be sure that the person already have your lunch, okay? Because I think it just will give the body the energy that you need to function, okay? So now I have been talking about glucose. Now let's add an extra word, glucose metabolism. Glucose metabolism is as simple as the process by which the body uses glucose to produce energy, okay? It's as simple as that. It's just the process that we use to produce energy using glucose, okay? And this is essential for every activity in your day-to-day. The glucose and the energy that we produce is important for dancing, for running, for thinking, even to be in love. We use glucose, okay? Because in this case, if you like or you don't like someone, if you are in love or not, requires glucose, okay? So it's a very important process in our body. So now that we talk about glucose metabolism, I would like to just introduce the next concept. And the next concept is about insulin. So let's connect glucose metabolism to insulin to start trying to answer why aging is a risk factor to develop type 2 diabetes, okay? So the first example that I have here is a healthy individual. So what happens in my body every time I eat a meal? So you can see here, we start with the step 1. We need to eat something. Now you know that the majority of the food in front of you will contain glucose, okay? So, or the digestive system will just digest the food, and we will have simple molecules like glucose. So this glucose will be absorbed by the intestine and then move to the blood, okay? So food, glucose, blood. If we are moving glucose to the blood glucose increases, right? Because we are moving blood from the food to the blood. So the consequence after you eat is that the levels of glucose will increase. But this is something very interesting, and I want to keep your attention in these cells. This is an example of your cells in your body. Most cells cannot take glucose, okay? I like to think like there is a door that is closed, okay? So how we can open the door? And this is why we need to start thinking in insulin. Insulin is a very important hormone that will be secreted by pancreas when the levels of glucose in blood increases. Okay? So the pancreas senses that there is an increase in the glucose levels, and the consequence is that we will have the release of insulin. And insulin, for me, is a kind of key. The key that can open the door of the cells. So what happens if we release insulin? Insulin will go and open these doors. The consequence is that now the glucose that we have in blood move inside to the cells, and the cells can use this glucose to produce energy. Okay? If insulin is not working well, we have in front a problem. Okay? Because there is no the key to open the door and let the cells move the glucose inside and start using the glucose to produce energy. Okay? So now I will show you here. So what happens if I have type 2 diabetes? So in this case, same case, you eat food, your digestive system will just digest the food, and the levels of blood, the glucose in blood will increase. The difference is at the level of the insulin, okay? So in this case, the pancreas will produce insulin, sometimes not the right amount, depending on the stage of the disease. But for simple words, we still have some insulin. The problem is that the key is not working anymore, okay? So this key is not able to open the door. What is the consequence? The first consequence is that the glucose will keep high here in blood. And this is the reason why high levels of glucose in the blood are a key characteristic of the type 2 diabetes, okay? Because the key is not working anymore and there is no way to reduce the levels of glucose here. But there is another important consequence, okay? In this case, we don't have the possibility to open the door. What happens if we don't open the door? Glucose cannot move inside the cells. Glucose cannot use the energy. This is why individuals with type 2 diabetes also often experience fatigue. Why? Because it's more difficult for them to use glucose and produce energy, okay? And we need energy for every single function in your body, okay? So let's stop here again. So the first part, I say that aging is a natural process that we all experience. I also say that aging is associated with a decline in how our body works. I also say that aging is a risk factor for developing diseases like type 2 diabetes. And now we are adding more things. I say that glucose is a molecule that is essential for your body because the glucose provides the energy for the body cells, okay? And also I say that insulin is a hormone that regulates the levels of glucose in blood, okay? Because insulin is the key to just open the door and let the cells in your body use the glucose. So let's go back to the first question that we have. How does aging increase the risk of developing type 2 diabetes? If type 2 diabetes is associated with problems in the glucose metabolism and is associated with problems in the insulin secretion, does aging affect the glucose metabolism and insulin function? Let's try to answer this question, okay? Now with all the understanding that we have. But before going, I will show you the origin of the data that I will show, okay? Because it's part of a research that I had the opportunity to be involved. So the research that I will show you has a name, and this name is Project 42. And the goal of this research was to develop the deepest data set possible for the study of metabolic diseases like type 2 diabetes, okay? If you want to know more about it, it's also called CHILAM. That means complex, okay? And it was a research where many people was involved, okay? And the first part of the team here, Dr. Steven, Rivera, Aston, and Fossion, are physicists and mathematicians. They don't know physiology, right? So the second part of the team involved in this research was Dr. Robles, Tapia, Hernandez, and Barajas. They are physicians. And I was in the middle, okay? Because I'm not here and I'm not here. But they were my colleagues teaching physiology in the School of Medicine in the National University of Mexico. And they were my colleagues working in my PhD, okay, in biophysics. So it was like the bridge to just, okay, what they want to say is this one. No, what they want to say, it just was a very interesting role that I had the pleasure to serve with this research. The other thing that I want to mention is that the research that I will show you was developed in the Center for Complexity Science at the National University of Mexico. This is the newest research institute in the National University of Mexico. And it was created because they believe that to understand complex problems, you need interdisciplinary research. There is no way to understand a problem if only visualize the problems is one point of view. You need to have many different points of view to evaluate all the different possibilities to be able to understand a problem, okay? This is the group that started this research. Right now, this research includes many different hospitals, many different, participants, universities, even this institute, the institute here, that is about genetics. Just to give you an idea about the research. And we say, okay, we would like to understand metabolic diseases, but we need to find a representative sample, okay? And we have the option to just go into every single state and just collect data, but it was a very expensive option. But we realized about something. Universities are a small-scale representation of the larger societies at the state of the country level. And we say, wait, we are in the National University of Mexico. We receive people, faculty, and staff for everywhere, for every single state in Mexico. So if we just use the population at the National University of Mexico, we can have a kind of representation of what is happening in a country. Okay, this is the power of the universities, okay? And the first thing that I will say that we collect as many information as we could. So demographic information, we measure many measurements related with anthropometry, physiology, genetics, and psychology. But the most important, we had the opportunity to collect data for a big range in terms of age. We have very young students, 18 years old, starting the university, to senior faculty members, some of them going for 70s and 80s. So we say, wow, it's super nice to have this whole range of ages. Let's start asking questions, okay? How is the glucose metabolism affected by aging? Now you know the characteristics of this population. So the first thing is that we collect blood and we measure the levels of blood, okay? So what you have here, this fasting glucose, means the glucose levels in blood in people who didn't eat a food between 8 to 12 hours. It means fasting, okay? So we just collect the blood, and I'm pretty sure you have been involved in this kind of test before, okay? So we have the levels of glucose here, and we have different ages here, okay? 20s, 30s, 40s, 50s, 60s, 70s, and 80s. This is the data. Every single point that you have here represents the measure of a single individual, okay? And you can see it looks messy, right? So we use a method and ask, okay, fit what is the best fitting in all these data that we have. And the best fitting was a line, okay? This red line. So the blue line that you have here, I add this line just to measure how look when there is not relationship. There is not a slope, it's like this. But in this case, what you can observe that the best fit was something like this, that we call a positive relationship. What means a positive relationship? It means that here in 20s, the average were about 80. But in these 70s, 80s, the average is 130. You see? What he's saying in very simple words is that as you age, your blood glucose levels increase compared with those in younger ages. So the levels of glucose are increasing as part of the aging process, okay? And you can say, yeah, at least, but this is just the Mexican population. Well, before going there, no differences between women and men. In both cases, we observe the same relationship. Okay, the levels of glucose will increase as part of the aging process. It's only happening in the Mexican population? The answer is no. Here I show you a paper that comes from the National Health and Nutrition Examination Survey. That is a representative sample of US adults. And in this study, they involve non-Hispanic white, non-Hispanic Black, and Mexican American. And no matter the group that they analyzed, the results were the same. Young age, 98. Middle age, 107. More than 60, 114. So the levels of glucose in blood increases with age, okay? What about Korean population? Again, exactly the same data. We observe that with age, we have an increase, okay? And this is a beautiful study because you can see here the number of the individuals, 12 millions. It's a lot for human research, okay? And they were super careful to be sure that every participant in this research were healthy, okay? Another important consideration with this research is that some of the points were collected from the same person. Same person, different years, okay? And you can see that no matter that, we observe the same tendency. There is a tendency to observe an increase in the fasting glucose levels associated with age. What was very interesting here in this graph is that they observed that in the case of the men, the increase in the glucose increases first, and then they observe at a steady state. In the case of the women, they observe that there is an increase that is slower, takes more time, and continue going up, okay? This is a difference. However, in both cases, in very general way, we observe that there is an increase in the glucose blood levels associated with the aging process. But I want to keep your attention in one important thing. This is considered normal range. What it means? It means that, yes, the levels of glucose increases as part of the aging process, but still in a normal range. This is an important consideration when you want to think about diseases, okay? And diseases is we start having problems outside of what we consider this normal range. So it was a very interesting data, and we say, oh, wow, no matter if it is in our hands, the Mexican population, or the population in the United States, or the population in Korea, the data is super clear. We are observing a tendency of an increase, okay? So I showed you before that the glucose levels in blood depends of a hormone, that is the insulin, because it's the key that opens the door, okay? Is insulin working well? So to answer this question, we decide to estimate something that we call HOMA. In very simple words, HOMA means that HOMA is a simple way to estimate how well the body responds to insulin, okay? if the levels of HOMA are high, means that you need more insulin to regulate glucose, okay? Sometimes in a complex way, we call insulin resistance. But it means that you need more insulin to regulate the same levels of glucose, okay? Simple as that. This is the data. And again, I use this blue line as a reference. If there is no relationship, we have a blue line. If we have a relationship, we have a red line, and it was a significant change. So wait, the levels of glucose are changing, but the levels of HOMA are changing too. What it means? It means that every year, you need more insulin to regulate the same glucose values. We need more insulin, okay? But something that really keeps your attention is that the variability of the data when we start working with HOMA. And we say, wait, you see, even in very young ages, we start having high numbers. High numbers is not great because it means that you need more insulin to regulate the same level of glucose. So we say, okay, let's understand what is happening here. The way that we estimate HOMA is associated with glucose, with fasting glucose, but also insulin. How look insulin? And this is how look insulin. So what you have here is the basal insulin, and you have age here, okay? Not significant. What it means, no relationship between insulin and age. And we say, okay, why? Why we are observing these changes? And we like to observe and observe. We have meetings, hours and hours, just observing the data and start thinking what is happening. And something that kept our attention was this point. This is the graph that I showed you before, okay? When we have the fasting glucose with age. You see how the majority of the points at 20s are together? What happened here in the insulin? They are not together anymore. So what we say that the basal insulin level shows a high variability even in very young individuals. And we say, why? Let's just see how much insulin you need to just regulate your glucose levels. And we found this paper. This paper is the Pastrana, and it's just in Mexican population because the data that we wanted to understand was Mexican population, okay? And in this research, they observed that a healthy individual, 30 years old, that are healthy, they usually requires about 7 units per ml of insulin. With this number here, just think about 10, okay, to simplify my life. So I trace a line here. So what you have here is that a really good percentage of the individuals here are producing more insulin even in very young ages. Very young, they are 20. We don't consider even, part of the aging process, and they are already having really high levels of insulin. Their body are using more insulin to regulate the same amount of glucose. And we say, okay, type 2 diabetes is most commonly diagnosed in people over 40s. What means this data? It means that you have at least 20 years to prevent changes. One important consideration when we observe this data. Where are these individuals in 20s? University. University years are an important opportunity to prevent or delay metabolic disorders because students are here in our hands. And this is just the first step when we can just prevent the development of type 2 diabetes. Okay, first thing, but not the main thing. So let's have a summary at this point. So what I show you is that the fasting glucose tends to increase with age. The second thing is that HOMA, that is just a simple way to know how insulin is working, also increases with age. We observe that basal insulin do not show an increase with age. However, what we observe is that there is not a relationship with the aging process because insulin levels are elevated from 20s. Okay, we start having a problem and we say, wait, now we have a problem. Is aging or is something else, right? Because we are talking about 20s. 20s is not considered, an old age. So how much the glucose metabolism change correlate with age? Are there other variables that we should consider? So I will show you here that are there other variables we should consider? And the answer is yes. What other variables? Lifestyle, diet quality, physical activity, if you are smoking, alcohol consumption, sleep duration, sleep quality, chronic stress, genetics, psychology, and many more. Okay, almost every single part of your life can impact in a positive or in a negative way the glucose metabolism. So we say, okay, now we know that aging is a variable, but we would like to understand also what other variables can just impact with the glucose metabolism, okay? And again, we went back and tried to just read, and we found papers for Rose and Mirowski. And they say that education teaches individuals to tap the power of knowledge. Education will have a positive impact in health. And did you remember that the main population we were trying to understand was National University of Mexico? We have the degrees. What if we just graph now insulin and HOMA based on the education and use education as a proxy of the lifestyle, okay? Because according with the research of these two authors, when you have education, you will have better lifestyle, better life quality, associated with better quality in food, physical activity, sleep duration. We can discuss about the chronic stress, but economic stability. It also will give you the opportunity to have better quality in terms of sleep, in terms of physical activity, in terms of diet quality. So we say, okay, let's use education as a proxy of lifestyle. It's not perfect. We know that it was not perfect, but it was just an approximation, okay? And just we wanted to see how look these relationships. And what I show you here, I will show you insulin first and then HOMA. That in both cases, it's just knowing how this hormone is impacted, okay? The function of this hormone for the glucose metabolism. The very first steps here is elementary education. So the participants with only elementary education, and we go for the PhD education. So we have a range between 1 to 5. 1 is elementary education, and 5 is PhD education. What do you think will be the result? Before we observe a positive relationship, right? We observe the opposite. We observe that it was a relation like high education, PhD education, just show less levels of insulin. What about HOMA? Exactly the same, in the opposite way. So how we interpret the data is that higher education correlates to significantly better metabolic health. Why? We still are trying to understand. Right now, what we think is that this education can be associated with a better life quality, okay? But we are still trying to understand. We don't have like a perfect answer at this point. But just having education as a proxy for lifestyle show us that higher education really correlates with better metabolic health. So what it means is that we can have better metabolic health, yes. Is this a possibility? Yes. So metabolic health at the end, during the lifespan, is associated with a component that will depend of the age, but also a component that will depend of the lifestyle. And I think, this is my very personal opinion, that we still need to understand better this situation, because I think there are many more things that we need to explore to understand the problem. Remember, complex problems requires interdisciplinary research, okay? So now with all these things that I have been just showing, how does aging increase the risk of developing type 2 diabetes? That was the first question in this seminar. Is that the aging process impacts the glucose metabolism? Okay, we observe an increase in the glucose levels. Also, it's associated with changes in the insulin secretion and insulin sensitivity. So it's more difficult for our body just recognize the hormone to regulate the glucose metabolism. So in consequence, it's more difficult for the body to regulate the blood glucose and the glucose metabolism in old ages, okay? It's more difficult. It doesn't mean that it's not possible, because aging, remember, aging is not a disease. You can still have this healthy aging, okay? And it's only happening in humans? No. And I love a lot this figure. This is a figure that I took for a paper of Yakuro in 2021. And what I show you here is a window, okay? This window, how is the glass?
Shattered.
Broken, right? This window represents blood glucose and age, glucose metabolism. And you can see that no matter if you are mouse, a monkey, or a human, they are all taking the hands. Glucose metabolism is part of the aging process. Some impairments in the glucose metabolism is part of the aging process, even in these three, okay? And why this one an important consideration for me? Because I had the opportunity to work and trying to understand human physiology. But I realized how difficult it is, okay? And also I realized that we cannot answer many questions just working in the human population, not in terms of the cellular or molecular mechanisms behind the aging process. And I say, okay, I know how to work with animals models. So in my research now, I'm using a model here and using my understanding of the glucose metabolism and the aging process to now move this question to a more simple model. And in this case, we have young ages, middle ages, and old ages. Why? Because 20s, 40s, and 65s was a key point for our research. So in my models, we are using 3 months, 12 months, and 24 months. And now we are trying to understand the cellular process here. So we have here a mouse. They have also pancreas, like us. They also have these pancreatic islets, like us. We have pancreatic beta cells, like us. These cells, the pancreatic beta cells, are the ones that release insulin. So I want to understand how aging impacts the function of these cells, okay? And this is what I have been doing in the last 2 years in the biology department at ISU. And I'm super proud that we have a lab. Here is a picture of all of them. And we are working hard to understand the cellular and molecular mechanisms behind, okay? Because this is a huge gap in knowledge. We still need to understand many things before say, oh, I got it, I understand the problem. I don't think we are at this level, not at the level of the aging process, okay? Here I show you some of the data that we have been doing. And for example, here is data from Daniela. Daniela is there as some master student in my lab. And we are creating models of the structure. This is a model of the pancreatic islet. And we are trying to understand, for example, how blood vessels and changes in the blood vessels can be associated with the aging process. We think that maybe there are changes in the vascular system that is the reason why we start having problems with the insulin secretion. And that maybe this is one of the reasons why we have the high risk of develop metabolic disorders. But also we are creating computational models because I learned that it's very important to have the power of prediction. And a way that we can have the power of prediction is to these computational models. So in the last paper of the lab, we just work with Gerardo Felix and my undergrad student, Danny, and we just have different, what you can see here, these green points that you have here are pancreatic beta cells. And these red lines are blood vessels. So we are trying to understand again how this system works in 3D. And we think that if we are able to just understand this system with computational models, we will be able to predict better. Is there a broken point? There is a point when we have changes and then we cannot stop. What is the best change to just start thinking in just delay the glucose metabolism changes? Okay, so right now we are trying to understand also and working with anti-aging treatments. That was something that I had the opportunity to work as a postdoc at University of Washington. And we realized that sometimes when you treat the animals with some drugs or even with the calories restriction, that is when you reduce the calories in your food, we can just delay the aging process. Are we able to delay the changes in the function of the pancreatic beta cells? If we delay, are we able to just improve the glucose metabolism as part of the aging? So I think these are the questions that we are working right now and trying to understand what is happening as part of the aging process and the development of metabolic disorders. So I have to say thank you to students, faculty, and staff from Biological Science Department. It is an amazing department to just be and be part. The Keck Center at University of Washington that gives us the opportunity to just IMARIS. But I have a good news. We will have IMARIS and ISU for the first time very soon. So we have a lot of potential to just develop models to the molecular research core facility and all these different, hours that gave us the money to start doing the experiment. But also I have to say thank you to my family. It is my mother, my father, my husband, and my little one. Because sometimes when you think you are not good, when you need a push, it's really good having someone, okay, that just push these efforts. And I would like to share something. This is Dr. De La Cruz. This is Liz. I am a chinelo, okay? And my custom of chinelo was created in 2012. You see the colors? So blue, orange, and black are and has been my colors since I remember. So it's very curious that now that I'm here and I ISU, the same colors, right? Orange and black. So just curiosity things. Open to questions and discussion, guys.
Well, I guess I'll go. That was so fun, Liz. Really exciting to see all the work that you've been doing, or not all the work, but some of the work you've been doing while you're here. So I was wondering about, how do you take into consideration, like this was obviously the broad population that you were showing a lot of data on. How do you take into consideration the family history or other factors that might contribute to?
Yes, yes. Even I'm not part of this research, but Dr. Stephens now is using genetics to also estimate how much this genetic part can be associated with. That is very interesting because they also hire many people. And the most interesting part for me was they hire a person who used to work in marketing of the soft drinks. Because they study us to be success with marketing. So now a marketing person is working as part of this research to also understand how other variables can be part of this research. Yeah. And the reason why they call 43 project is because they estimate that for the development of the obesity requires at least the change in 43 variables.
Wow.
So they think that it's a variable.
Multivariate, yeah.
Exactly.
There's actually a professor at Georgia State University who joined while I was like finishing up there. And Coca-Cola headquarters is also in Atlanta. And he worked at Coca-Cola he worked as a scientist there, and he was studying obesity in terms of Coke. And then he decided, I'm going to not stay in industry anymore. I'm going to go back and look at, because, like Coke only is going to publish what they want to. So then he went back to this. You don't hear about that transition very often, but he went back to Georgia State and he's studying obesity and not influenced by Coke.
And this is very important because I have been talking about the glucose metabolism, right? Glucose. You can find glucose everywhere in your diet. And I think, and I have heard for people like glucose is bad, sugar is bad. No, glucose and sugars are very important components for the body, okay? The problem is not the glucose. The problem is not the sugar. The problem can be associated with an excess, for example, okay? So I think we need to just understand the problems in many different points of view. And this is why I really appreciate having the opportunity. It just changed my mind in how I can visualize a problem. I think I cannot able to think in a problem since one or two perspectives anymore. I also asking people like, okay, what are you? What about you? Because every single person will give you a different perspective and can just give you the ideas that you never, imagine. Thinking in a research in metabolic diseases, never in my mind was like, I will hire someone for marketing, right? But when I talked with this person, I was impressed, like, wow, I didn't know all the process, all the science behind, marketing that is associated with brain function, psychology. And I was like, wow. Now I think twice every time that I observe something. It's like, no, they're not playing with me, right? They are just playing with my brain.
Can I
So,
go?
yes.
So first of all, thank you for this wonderful presentation. I have always been curious about your research, and today it was really a good opportunity to know about your research. Mine is basically a general curiosity. So you had said, right, like in the 20 years age group, the basal insulin level was high and the glucose metabolism was like the average level, right? So would there be any correlation between the insulin level and then the glucose metabolism at that age group? And also, does this mean like higher insulin level means like the glucose metabolism is working properly? Does that also apply to the aging population?
Thank you for these two questions. I think are great. Let me just go back here because what you are saying is very, very important. So if you remember when I showed you the first part of the seminar, I show you the relationship between glucose and insulin, and that we cannot use glucose if we don't have insulin, okay? So what I think is happening is that the body is able to keep these levels in glucose in a normal range at the expenses of the excess of insulin secretion, okay? So what I think is that the body is like, okay, you are not eating well. It's okay, I can manage it. But 1 year, 2 years, 10 years, after 20 years, the body will say, I'm sorry, I did my best, right? And now is why even 40s is the age where majority of the type 2 diabetes is here, right, diagnosed. Because we push too much the system. And I didn't show you data, but this research, we also publish a different paper when we create a network. We call the metabolic network. And we see this metabolic network at 20s and 30s and 40s and 50s. And the surprise is that 40s is when the network collapses. Again, 40s. At least 20 years to prevent. So the network, so the body is able to compensate or bad habits for a time. But remember, aging is associated with a decline in function too. So, okay, the body is like, okay, I'm out. And at that point is when we start having the development of diseases. So, but I think it's a consequence of both aging process, that is a decline in function associated with, the loss of compensation that we were lucky to have here.
Yeah,
So
thank you.
let me go ahead and then, yes, Luisa.
Thank you. So first of all, I really appreciate the way that you present, not just the presentation, but the way that you present is very didactic and very easy to comprehend. So that's something that I have to recognize. And I have
you.
2 questions, and I am going to pose them in the order that I think is easier to answer. So first, how do you, and this is just a general curiosity, how it's going to be translated, the research in mice to, I assume, apes to eventually make it into humans? So that's the first one. And the second one is, so when you said that in the I think in the first study that you explained, you said that you were using education as a proxy for lifestyle. And I'm very curious of the use of proxies in science. And this is somehow related, and this is big and not necessarily a specific question, but have you or have that group think about also the use of structural barriers? Because we know that there is a population, especially especially with the access of the Latin American public university, which is very different than the public university in the United States. What's the population who can have access to university? What's the population who can have access to spare time to cook and have physical activity and stuff like that? So how have you thought about including that?
I was not ready for this question, but I have something, right? So yes. So the truth is that type 2 diabetes is a disease that in the last years has been considered a disease or a problem of, economical stability. Access also to a physician, access to good quality of food. And for example, you can see that the prevalence of type 2 diabetes change between groups. And unfortunately, American Indian of Alaska here, Black, non-Hispanic, Hispanic overall, are the 3 with higher prevalence numbers. So what it means is that, yes, it matters. Having the opportunity or having access to health matters. And the groups that usually don't have as much, possibilities to just even detect with time are the ones with highest prevalence. So yes, I think, but it could be here, but not necessarily even thinking in the different population. It's just having access or not is a problem, right? Because the ones who will have the access are the ones with less prevalence. This is why we think that education, that in part having this negative correlation with education is because when you have more and more education, you will have better understanding, better knowledge about something, but also better economical stability that will give you the access, right? To just check every year, how is my glucose levels? How is my insulin? Have the opportunity to just visit the doctor every year, as a checkup point. And about the second one, the first question, because I answered the second one first, is how we can translate. This is what we are trying. For example, my lab is trying to understand the aging process and the sympathetic nervous system. The sympathetic nervous system is part of the nervous system. the one that regulates the function of every single organ, okay? And there are some drugs that has been used for the regulation of the sympathetic system. But we don't know how the sympathetic nervous system change as part of the aging for the insulin secretion. If we are able to understand how works this system, we are able to propose, for example, different targets. What if the sympathetic nervous system is a target for prevention or for delay changes associated with the glucose metabolism? Another important point is that unfortunately, when we are trying to understand aging in the lab, we usually have young and old ages, and we don't have what is happening in between. This is a huge gap in knowledge. And why is important to understand what is happening between young and old? Because if we want to prevent, we need to know where the changes will start. So we are trying in our lab, working with different ages, trying to know where is the age where these changes will start. And if we know, I think we also can just visualize the problems in a different way. Because I don't think it's a good idea, and it happened with the anti-aging treatments. If we use the anti-aging treatments with the problem is already there, it's even worse. If we use the anti-aging treatments at the right time, we can see an improve in health. So I think this is the other important thing. So we are thinking sympathetic nervous system, and my lab is trying to find where is the right time. Where is the time that everything will start changing? And we can just translate this one to humans at some point, I hope. Maybe not. It's basic science, right?
Great talk. I have a question about kind of the Korean study. And so for the data that you showed where there's the high variability in the basal insulin levels in early, like in 20s and 30s, have you found that these levels are maintained as high or maintain that high variability for those same individuals across time? Or did they find that in the Korean study? And would that potentially indicate vectors for early intervention in people that are in their 20s and 30s to detect and say, hey, in 20 years, this might become an issue. Here's how to adjust that currently, even though those are within what you call normal levels?
That's a great question. So trying to just pointing out this problem, Alice, the group of Dr. Stevens is trying to create a model, a mathematical model. And every year I have seen that they are more and more variables because they want to have the power of prediction. It's like, yes, you have, normal glucose levels, but this is your diet. This is your quality, your sleep quality. This is the quality here. This is here. And right now, the model is able to predict what age you will develop a disease based on your data at 20s and how you are just, managing all these things. What is very interesting from this for this model that Dr. Steven is working is that there is a ways to move things back. But we don't know at what point this is not possible anymore. So yes, the idea is here, for example, you can see that this is a different data. According with the network that will create the metabolic network say that at 40s, we completely change. Our body just, this network is not the same network anymore. But if you can see here in different data, different population is suggesting the same, we will start having problems at 20s. And as soon as we don't know if there is something that we can keep and then moving back, or there is a point here where no matter what, you cannot just moving things. So yeah, I don't know. Would you answer the question? Yeah, so let's see, I'm very optimistic and waiting for the model of this group. And I'm hoping that at some point we can also have a kind of similar research on ISU and trying to understand also how the population, here works in terms of many different, variables. It could be nice to have something and understand also Idaho population, because I have been trying to just know more about the Idaho population in a very specific ways, and it's not super clear to me. I mean, there are some information, but I think it's not good enough to start estimating and predicting things. Yes, Dee.
Yeah, there are actually a few studies that people are doing across campuses to measure stress level in some way. So where participants have to take their hair and submit that as part of the process, and at any time, in the day, they might get a message to report how they're feeling with stress, for example.
Yeah.
And answer very quick questions. Have you eaten yet? Are you stressed? To rate these things and then submit. They give them a little kit with things to mail back to them. There's a study out of UT Austin. There's studies in Wisconsin as well. I know these things are happening.
Yes.
And I mean, I
think it's important.
It's important.
And do you know what? I think something that I learned from this study is that another factor that is very important is just trying to have as many variables as possible at the same time.
Mm-hmm.
And this is very difficult.
Yeah.
Also, sometimes it's very difficult to convince a person, hey, join my research, and they get
For a
reluctant,
longitudinal
no,
study.
right?
For humans, that's one of the biggest issues is to get.
But this is the beauty of this research, that they are trying to collect as many data as possible of the same individual.
Mm-hmm.
And in fact, when I was working in this research, we took many blood samples, and these blood samples are still now distributed to many different hospitals and research institutes, just trying to have even more and more and more from the same, because we already know this population, and just adding more and more and more will just give more value to the prediction. At least I say 43 variables are the ones that needs to move to start thinking in a disease development. 43 is, for me.
Yeah. I mean, these days doctors do have, I don't know exactly what their algorithm is, but they will plug things into a program that will spit out the risk factor for certain things. And then they use that to give medication.
Yeah. But we need to increase more this number of variables to just make it these predictions better. But thank you.
So if you're diagnosed with type 2 diabetes, they prescribe metformin. What is metformin? What's the chemistry? What does that do in your body?
Oh, many things. But one of them is associated with insulin. It will just help to release more insulin to be able to regulate the glucose levels. It just helping your body to maintain the glucose levels in a normal range. Because it's a problem. Having high levels of glucose in blood will start damaging your organs. This is why it's super important just keep these levels of glucose in a normal range. So this metformin is just helping your body to just keep the blood levels through insulin.
I guess my question part of that was, what's the chemistry? What does it do to help increase the insulin?
It's at the level of the pancreatic beta cells. They just change something in the pancreatic beta cells, and these cells are releasing more insulin. Yes, cellular level.
Thank you.
Sure.
Is it a question on along those lines? So is it the drug that they're using? Does it contain maybe like what do you call it? A hormone that the pancreas uses or something to generate more insulin? Do you know?
There are many mechanisms. So I don't think there is one thing. But what I can say is that only helps to release more insulin. Yeah. Also, there are some evidence that works at the level of the liver. Also, they say that also modifies brain, other modifies, kidney. So there are many things that has been associated with the function of this drug. It's a very complex drug.
Thank you, Dr. De La Cruz. Much appreciated. And thank you all for attending. Much appreciated. Good to see you all. Just getting in a quick plug. We will have one more faculty lecture series event on April 2nd at noon, also in this room. We have Dr. Daniel LeBrier talking about nuclear energy and everything you were afraid to ask. So yeah, I hope some of you can join us for that as well. Thank you all.
Thank you.
Good day.
How are things?
Busy. I have a very packed day. Very, very, like, a lot. I just texted it
I
to
mean,
you.
I
But like, remember you told me.
political scientist, I'm a STEM scientist. And that was about the perfect level of.
I'm just telling you
Down to my
that.
level.
Like,
That was
I
perfect.
just.
Because I was super worried. I wasn't
You
sure
did a fantastic.
how
job.
to.
That's why.
Yes.
I was.
April 2nd,
Amazing.
Talk to my
Right.
biochem class. A player.
Yes.
the next,
Oh, yeah, I'm sorry. Do I have your email?
yes.
Okay,
April
I will
2nd.
probably send out another announcement in about a week for that one. But yeah, April 2nd, which is a Thursday at noon.
Okay, thank you.
Yep. Send that one too.
I didn't see
If
you at first until
fasting,
you asked.
individuals fasting.
Yeah.
I was like, yeah.
Nuclear.
I didn't